The first thing that we're going to talk about today is effective values of periodic signals. And whether you know it or not, you may have already been using these. So I'm going to draw one of my terrible pictures here. And just to make sure we're all catching what I'm throwing, I'm going to explain what it is that I am trying to draw. I am simply trying to draw a receptacle like you might find here in this classroom or in any of your homes or anything like that, okay? So it should look vaguely something like this, okay? And what we'll see is that there's a slot for a large blade to go in over here, usually a different sized slot over here, and then something that looks like this. Okay. So on one of these receptacles, this bottommost place that something can go in is where we have our connection to earth ground in our home's electrical network. Okay. So this is our essentially how we connect to our ground wire. Then this guy over here is our connection to the neutral bus of our load center or circuit breaker panel. And then this guy over here is how we connect to our hot bus of our circuit breaker panel. Okay. So essentially, whenever we plug something into a receptacle, it's receiving voltage from its connection to the hot bus and the neutral bus, okay? So what I want to ask you guys is simply, what voltage do we see across the terminals of a receptacle in our homes, or something like that? Anybody know? So I hear most people saying 120, a couple of people say 110. Those are both commonly referred to voltages. So everybody that said 120 and 110, you are both right and wrong at the same time. So let me explain what I mean by that, okay? So is the voltage that's provided by one of these receptacles a DC quantity or an AC quantity? It's AC, okay? So if we hooked up an oscilloscope to this guy, we would see that it is a sinusoidally varying voltage. And that sinusoidally varying voltage actually ranges all the way from just shy of 170 volts to just shy of negative 170 volts. So as our voltage as a function of time, if I'm remembering correctly, my math might be slightly off, it'll come out to be, I believe, about 169.7 cosine 120 pi t plus whatever phase we happen to have whenever we start looking at our signal, okay? We tend to refer to this, so I'm going to put some is approximately equal to, and then a question mark over it, 120 volts, okay? Where 120 volts, most of us would probably think of this as a DC quantity. And realistically, that 120 volts does refer to a DC quantity, but we're leaving off a little bit of information there, okay? So that 120 volts that we commonly call the output of one of these outlets is actually what's called an RMS voltage. So realistically, we're just leaving off some subscripts from our unit there, RMS. RMS stands for root mean squared. And here in a couple of minutes, when we introduce some math, we'll figure out why we're calling these RMS voltages and all of that kind of good stuff. So that 120 volts RMS is the effective value of that periodic voltage waveform, okay? So I want to give you guys kind of a formal definition for what an effective value is here, okay? So an effective value is a DC equivalent signal that delivers the same amount of average power as a periodic AC signal of interest. And so I want to put a little caveat here. When I say a periodic AC signal, I am not just referring to sinusoidal signals like we deal with in our everyday lives. This could also be square waves, triangular waves, literally any type of periodic signal that varies in time. You can determine the effective value of that signal by finding out essentially how much average power it provides to a particular load, and then back calculating to find out what the DC equivalent signal would be. And so we're going to talk about what that process entails here really quickly, okay? So let's consider that we have a simple resistor, right? Because we know that capacitors and inductors don't absorb any average power, so the result of that math is always going to be zero, so that's not really helpful here. Let's say that we have a resistor, okay? So on the DC side of things, I know that the average power provided by a resistor is just my DC voltage squared divided by my resistor value. And in terms of current, that would look like my DC current squared times my resistor value. So if we had a generic periodic AC signal, I could say that my average power would be the integral from 0 to t of my periodic voltage waveform squared divided by my resistor value with respect to time. And then I need to take that integral and then divide the result by a factor of 1 over t. So this is exactly how we talked about finding the average power for any periodic signal formally at the end of Wednesday's class meeting, right? So that V squared over R is just simply our power, where our voltage is now a time varying function. We are taking the integral of that assumed periodic signal over one period and then dividing by the length of the period, which is again exactly how we talked about formally finding the average value of a function in class on Wednesday. So pretty similarly, I could say that my average power is going to be 1 over t times the integral from 0 to t of a periodic current waveform squared multiplied by r dt, like so. So what I'm going to do here, and this is really only going to take a couple of steps, is I'm just going to put these two relationships for average power and set them equal to each other, and then I'm going to solve for the DC voltage and the DC current, because our effective value is the equivalent DC voltage or current that delivers the same average power as our AC signal, okay? So if I put these two guys equal to each other, so I'm going to call this V effective squared divided by R. because I'm trying to solve for this effective voltage, and it's playing the role of our DC voltage in our system. And I'm just going to make that equal to 1 over t times the integral from 0 to t of v squared over r dt. And I hope that we can all very easily see there's a common factor of 1 over r on both sides. So that means the size of the resistor literally doesn't matter at all, okay? So now I just have effective voltage squared is equal to 1 over t times the integral from 0 to t of my periodic voltage squared. So I can just take the square root of both sides, okay? And so that winds up giving me the relationship. My effective value for my voltage is equal to the square root of 1 over t times the integral from 0 to t of the square of my voltage. And we could follow an extremely similar derivation. I'm not going to make you guys go through it. And we would find that the effective value of our current is really the exact same thing, except that we're just going to replace our periodic voltage waveform with our periodic current waveform. Okay? So this is how we find the effective value for a voltage or current, and it's literally the exact same mathematical expression, so it's really just how we find the effective value for any periodic signal. So let's talk about what math is actually going on here, okay? So what we are doing is we are taking the square root of the arithmetic mean. Arithmetic mean is just a fancy word for average of the square of our signal of interest. So that's why we have units of volts RMS. That RMS literally tells us the math that we did to get there. We took the root of the mean of the square of the signal in order to come up with that effective value. Okay. So I want to work a couple of examples here, maybe just one or two tops because we're a little bit pressed for time, to show you how to utilize these particular equations to find the effective values of things, okay? And then we're going to move on to how this concept is actually used, particularly in power calculations and all of that kind of stuff for AC systems, okay? So let's start with something like this, okay? So let's say that I have some voltage signal V of t. And let's say that that part there is 4 volts. This point here is 2 volts. And let's make this 0, 2, 4, 6, 8, and so on and so forth. Okay. So let's say that I have a brief rectangular pulse followed by a linear decay like this. Then it stays 0. And then that particular waveform just repeats itself over and over and over. Okay. So is this a periodic signal? Yeah, it repeats itself at regular intervals, okay? So what is the period of this particular signal? Let's say that time here is measured in seconds and voltage here is measured in volts. So what's our period? 4, okay? So we can see just by inspection that our period is 4 seconds, okay? So if I were to try to mathematically describe this signal over one period, I could say that this is going to be a piecewise function, right? Because it's got 3 distinct things. So to me, this looks like it has a value of just exactly 4 volts over the interval from 0 is less than t is less than 1. For that second interval, which is from 1 is less than t is less than 2, it has a slope of -4. So I'm going to put -4, and this would be having units, particularly of volts per second. And then I'm going to do, let's see, it's time shifted by 1 unit to the right. So that's going to be t minus 1. And then it has an intercept of 4 volts. And this is valid from 1 less than t is less than 2. Before we move on from this, because I'm sure some of you are like, what the hell is he doing to get this? That's fair. So when I see a straight line or something like this, I treat it as if essentially this new point, which corresponds with t is equal to 1, is kind of like my new origin. And I've just shifted everything over 1 unit in time to get there. So I'm just putting this in the y is equal to mx plus b format. So my slope is -4 volts per second. My intercept at this new effective 0 point, t is equal to 1, is equal to 4. And then for my variable, since I shifted to the right by 1 unit, I just subtract 1. So if we plug in t is equal to 1 here, we should get -4 times 0 is 0 plus 4, so it comes out to be exactly 4. And at t is equal to 2, we would have, let's see, -4 times 2 minus 1, so -4 plus 4 is equal to 0, so it works out, okay? So that's just me trying to explain something about time shifting, which again, I think you guys were supposed to have learned probably in your pre-calculus classes and all that kind of stuff, but I understand it's been a hot minute since you've had to apply it, so just reminding you how that works. And then lastly here, we would see that our voltage is simply 0 volts over the interval from 2 is less than t is less than 4, and then this repeats over and over again. Okay. So how I would find the effective value of this periodic waveform is I would literally just put this stuff into my equation, okay? So because I have a piecewise function, I'm going to need to split my integral up, okay? So I would have the square root of 1 over t, which is 4 seconds, multiplied by the integral from 0 to 1 of 4 volts quantity squared, plus the integral from 1 to 2 of -4 volts per second times t minus 1 plus 4 volts, that whole thing squared, plus the integral from 2 to 4 of 0 volts squared dt, like so. And all of this is under the square root sign, okay? So I think it's probably really obvious to all of you, but this last integral is just going to come out to be 0 because I'm integrating literally the number 0 over some fixed interval. The only reason that I included that is so that I could show that overall our integration starts at t is equal to 0 and it ends at t is equal to 4. So we are integrating over 1 full period. We're just breaking up that period into smaller intervals because our voltage changes its behavior across those smaller intervals. Yes. Why did we time shift by 1? Because we have this new linear behavior over the interval from 1 to 2. So it's no longer a constant value, it's now changing in time. So I was just describing how it's changing in time. Okay. All right, so now let's do this here math, okay? So we would have the square root of 1 over 4 seconds. So that's just a constant 16 volts squared. So I could pull that out. And then I'm integrating dt from 0 to 1, which is literally just going to look like 1 second minus 0 seconds. So that's the result of my first integration, okay? For my second integration, I can't really do that part in my head super well. So I am going to probably wind up foiling this thing out a bit here, just so that we can see what happens, right? So here's 1, here's 2. Maybe I should do this on a separate page so I don't screw things up, right? So let me just look at this. So -4 t minus 1 plus 4 squared. So that would be -4t plus 4 plus 4 squared. Can we all agree with that? Okay. So that's the same thing as -4t plus 8 squared. And because my brain doesn't like that negative sign out in front, actually, I can work with this. So -4t times -4t is going to be 16t squared. -4t times 8t is going to be -32, and then I'm going to have another instance of that, so that's going to be -64t. And then 8 times 8 is just 64. So I believe I've expanded that out correctly, okay? So that's going to look like 16. So the units on that -4 were volts per second. So that's going to be volts squared per second squared, t squared, minus 64 volts squared per second, t, plus 64 volts squared, dt, like so. Get rid of all this stuff down here since we don't need it anymore. And now I should be able to do most of this integration largely here on paper, right? So we'd have 1 over 4 seconds. So 16 volts squared times 1 second is just going to be 16 volts squared times a second. Then I'm going to have plus. So let's see. So when I integrate t squared, that's going to look like 1/3 of t cubed, right? So that'll be 16 volts squared per second squared times 1/3 t cubed evaluated at 2 and 1. Then I'm going to have minus 64 volts squared per second. So the integral of t is just t squared over 2. So I'm going to throw a 1/2 t squared evaluated at 2 and 1. And then the integral of 64 volts squared dt. So I'm just going to have 64 volts squared times 2 seconds minus 1 second, like so. Close that guy off. And keep on keeping on down here. 1 over 4 seconds times 16 volts squared seconds. Let's see. So that's going to look like, let me just make this easier on myself. 16 thirds volts squared per second squared. And then that's going to be 8 seconds cubed minus 1 second cubed, right? Because 2 cubed is 8. Then I'm going to have, let's see, so negative 64 times a factor of 1/2 is just going to look like 32. Let me put that down in the middle. Volts squared per second. And then I'm going to have 2 seconds squared. So that's going to look like 4 seconds squared minus 1 second squared. And then lastly, 64 volts squared times 2 minus 1 is just going to be 64 volts squared seconds. So I hear whispering. Have I made a mathematical mistake, or are you guys just not catching what I'm throwing, or some combination thereof? What did I screw up? Yes. Huh? Absolutely. Yep, 100%. The equation is very much on the equation sheet. So, yep. So the 16 plus the 64 come out to be 80 volt second squared. Yeah, most of your calculators can actually just do this for what it's worth. So let's see. So this is going to be 16 thirds times 7, and the units here should be volt second, or excuse me, volt squared seconds. And then let's see, minus 32 times 3, and the units here will also be volt squared seconds like so. And let me just throw this noise into my calculator real quick. So we have 80 plus 16 thirds times 7 minus 32 times 3. All of that is divided by 4. Crap. Answer over 4. And so I wound up getting 16 thirds of a volt RMS. I did. Thank you. Yeah, that seems too large. Thank you for that. So square root of 16 thirds. Yeah, because 16 thirds is a little over 5, and there's no way in hell the average or the effective value of this thing should be larger than 4. That's impossible. So I totally just forgot the square root. Thank you for that. So let me just do the square root of that answer real quick. And so that comes out to be approximately 2.309 volts RMS, which makes more sense. Okay, so I worked a numerical example here. You are 100% right that for the most of the stuff I'm going to give you, you can actually just throw this in your calculator if you know how to make it do integrals and stuff like that for you. So I would definitely practice that if you weren't aware of it. I'm just mentioning that because I know for a fact some of you were not aware that your calculator could do that for exam 1, which would have made at least 2 of those problems real easy. So anyway, so all of your FE approved calculators can do integrals and can do derivatives for you as long as it's over fixed intervals. So it can't do indefinite integrals, but it can do definite integrals like we would have here. Okay, so I've shown you how this thing works. Now let's apply it to what we've been talking about, which would be a sinusoidal signal, okay? So let's say that I have the simple current waveform, I of t, is equal to Im cosine omega t plus some phase angle theta I. So this is just generic sinusoidal current. So we are going to do this generically. So we're going to figure out what frequency dependence we have, what phase dependence we have, what magnitude dependency we have, etc. Okay. So can anybody remember what the period of a sinusoid should be in terms of our angular frequency omega. 2 pi over omega, that's it. So my effective current here should be the square root of, let's see, so that's going to be omega over 2 pi, because that's 1 over t, times the integral from 0 to 2 pi over omega of Im cosine omega t plus theta I, square that dt. When I square that cosine function, that's going to leave me with following relationship. So that's going to look like 1/2 Im squared plus 1/2 Im squared cosine twice omega t plus twice theta I. And this is just using that exact same trig identity that we used in class on Wednesday when we were multiplying a cosine voltage function by a cosine current function. Okay. So I'm just going to split this guy up, much like we did when we were looking at average power towards the end of class on Wednesday. And I'm going to just have two integrals now. So I'll have the integral from 0 to 2 pi over omega of 1/2 Im squared dt plus the integral from 0 to 2 pi over omega of 1/2 Im squared cosine twice omega t plus twice theta I dt. And all of that goes underneath this square root sign. So my question to you guys is, what's the result of that integration? So you should be able to figure it out just by thinking your way through things, but I'm going to give you guys a real strong hint here real quick, okay? So let's just assume for my being able to draw this thing shiddily's sake, that theta I is equal to 0 degrees, okay? So here is our time axis, and then just for what it's worth, if our current is oscillating at some angular frequency omega, so let me just draw something like that. This distance from here to here is our t is equal to 2 pi over omega, okay? So this blue curve that I've just drawn is our signal that's oscillating at an angular frequency of omega. Well, the thing that we're integrating is oscillating at a frequency of twice omega. So that means that it should be repeating 2 cycles for every 1 cycle of our original signal. So it should look something akin to this. So what I'm asking you guys is essentially, what's the area that I just colored in purple? 0. Anytime we integrate a sinusoidal signal over an integer number of periods, and in this case, we are integrating over exactly 2 periods, The answer should be 0. So this whole thing right here is literally just 0. Okay. So what we're left with is just this other part right here. Well, 1/2 Im squared is literally a constant. So we can pull that out, and we have omega over 2 pi times the integral from 0 to 2 pi over omega dt. That's just 1 over t times the integral from 0 to t. We already know that's equal to 1. So essentially what we wind up getting is simply the magnitude of our current divided by a factor of the square root of 2. So this is a very interesting result, okay? And I'll explain why it's interesting. So the effective value of our current in this case, our sinusoidally varying current in this case, is independent of frequency, right? There's no omega in our end result whatsoever. So it doesn't matter if we are here in the United States, where we have 120 pi radian per second as our excitation frequency, or if we're over in Europe, where they use 100 pi radians per second as their excitation frequency, the effective value is just the magnitude of that current divided by the square root of 2. It's also independent of phase. The only thing that matters is our magnitude. So this means essentially that whenever you have an AC system anywhere in the world, you can analyze it in the exact same way. The fact that it's oscillating at different frequencies means nothing to us. It's always going to have the exact same effective value. Just take the magnitude, divide it by square root of 2. Yes, ma'am. So what we are going to do now is we are going to take this result and we are going to play around with some of our power relationships, and we're going to develop new ones, okay? So I want us to revisit our average power equation that we came up with in our last class meeting, okay? So what we found was, generically speaking, so for any AC network, our average power was found to be 1/2 times the magnitude of the voltage times the magnitude of the current cosine theta V minus theta I. That's one of the first relationships that we got in class on Wednesday. Okay. So what I'm going to do here is I'm going to split that factor of 1/2 up into 1 over the square root of 2 times 1 over the square root of 2. And that's going to allow me to distribute it a little bit. So we could say that this is Vm over the square root of 2 multiplied by Im over the square root of 2 times the cosine of theta V minus theta I. Well, in a sinusoidal system, Vm over the square root of 2 is just the effective value of our sinusoidal voltage. So I'm going to call that V effective. Im over the square root of 2 is just the effective value of our sinusoidal current. So I'm going to call that I effective. And then we're going to have cosine of theta V minus theta I. So this allows us to calculate our average power using our effective values for these sinusoidal signals. But we can go beyond this, okay? And so this is where things start getting a little wild and crazy. Because people much smarter than I recognize that that mathematical expression right there is actually just the real part of a complex multiplication, okay? So we know from Euler's identity that cosine represents the real part of an imaginary number, and sine is the imaginary part of a complex number, excuse me. So we could say that this result here is simply the real part of the following complex operation. So I'm going to put V, and this is going to be with a tilde over it. So this represents, instead of a phasor voltage, an RMS phasor voltage. And we're going to talk about what that means here in just a second. And then I'm going to have I as an RMS phasor current, and I'm going to conjugate that. And I have to do the conjugate Otherwise, I would have cosine theta v plus theta I, okay? So this quantity right here is what's commonly referred to as S, which is our complex power. Okay. And now we're going to pivot and explain where those RMS phasors come from, and then go into much more detail about this concept of complex power. Okay. So I'll give you guys a moment to catch up writing this, and then we'll move on in a moment. Yes. It's an RMS phaser. I'm going to explain how we get our RMS phasors and all that kind of stuff here in just a second. I'm sorry, what? That is the real part, RE. Okay, so I'm going to move on to the next page, and let's talk about complex power. So all of our complex power calculations are going to be done using RMS phasors. So I want to make sure that you guys can accurately find your RMS phasors when you're given any information, okay? So I'm going to start with a time domain voltage, okay? So Vm cosine omega t plus theta v, okay? Now, the exact same process can be used for currents. I'm not going to bother writing it down because it's literally the exact same thing, okay? So just know that it can be used for currents as well. So we've already talked about this guy right here. This is a time domain signal. And we hopefully know that working analysis out in the time domain is an utter nightmare. So in order to avoid that, electrical engineers came up with a concept of phasors, right? So we could represent this time domain signal as a frequency domain signal or a phasor voltage V by simply taking the magnitude of that voltage, taking the phase angle of that voltage, and throwing the rest away, right? So this is our frequency domain. Signal, also commonly called a phasor. That's what we've been working with over the last couple of class meetings. And now what we're going to do is we're going to take this one step further and develop our RMS phasors. Okay. So I'm going to say that my RMS phasor voltage, so it will have a tilde over it instead of a bar over it. And you will also see RMS phasors will always be expressed with units of volts RMS or amps RMS. So there's two different ways to make sure that you know what you're dealing with. Is simply going to be our phasor voltage divided by the square root of 2. That's literally it. So what that gives us is effectively Vm angle theta v over the square root of 2, which is nothing more than V effective angle theta v. So these are how we're going to describe our signals in the RMS phasor domain. So once again, and I'm going to put a note here. Units are volts RMS. So if you have a problem, and this is more on the homework side of things, where you're given units of volts and you're asked to do any sort of complex power calculations, the expectation is that you will convert your voltage phasor into an RMS phasor simply by dividing the magnitude of it by the square root of 2. Or you could do everything out and then just multiply your final answer by a factor of 1/2, and that'll get you the same result. But anyway. Okay. So Now let's talk about this complex power thing. So we're going to say that S, which is our complex power, its fundamental definition is simply going to be the RMS phasor voltage multiplied by the complex conjugate of the RMS phasor current. Okay. So I'm just going to make a couple of notes down here. This S is our complex power. This is a trick question. I'll get to you in just a second, Real. So this is 100% a trick question. What are the units of complex power? You're wrong. You're right, but you're also wrong. So I told you it was a trick question. There are units. So this is where things get wonky, okay? The units of complex power is the volt ampere. So we all know that a volt times an ampere is a watt. But watts are what are used for average power, and complex power is different. So we use the made-up unit of volt amperes to distinguish between average power, which is measured in watts, and complex power, which is measured in volt amperes. So dimensionally, it is the exact same thing as a watt, but we call it a volt ampere so that we know we're talking about complex power, okay? So the units of complex power are the volt ampere. Brielle, what was your question? Root mean squared. So if complex power is defined as the product of the multiplication of two RMS phasor quantities or two complex numbers, then that means our complex power is also a complex number, okay? So that means that we can express it in rectangular form or polar form, okay? So I'm going to work on the rectangular form expression first, okay? So in rectangular form, this is going to look like the magnitude of our RMS phasor voltage, which is just V effective, times the magnitude of our RMS phasor current, which is just I effective, times the cosine of theta V minus theta I plus J, magnitude of our phasor voltage, magnitude of our RMS phasor current, sine theta V minus theta I. Okay. So this part right here is literally just our average power, which we already know is usually expressed in watts. And I'm going to give this average power a symbol, P. You might see it as P average, but usually I'm just going to write it as P. Okay. So our average power is the real part of our complex power, which is exactly how we defined it up here. Okay. And it essentially represents the portion of our complex power that is capable of performing mechanical work. Okay. So it's essentially the part of our complex power that winds up getting converted to heat eventually by resistances and stuff like that. Yes. It is indeed. And we'll get there in just a second. Yeah. So the imaginary part, as Matthew just mentioned, is what's commonly referred to as reactive power. Okay. Reactive power is measured in volt amperes reactive. So we now have a third different unit to use when we're dealing with complex power. I'll get to you in just a second, Carter. The symbol for this is typically expressed as Q, and reactive power is associated with reactive elements in our system, like inductors and capacitors. So what the reactive power really represents is how much temporary energy storage we have in our system. So it is not by any stretch of the imagination actually an imaginary quantity. It's simply 90 degrees out of phase with our average power, okay? So it is absolutely critical for our systems to work, okay? Without having reactive power in our systems, our electrical grid would have constant failures and constant blackouts because the presence of reactive power effectively helps our system to ride through voltage imbalances and stuff like that. So without it, if we had too much of a load being drawn at the same time, the voltage from our generators would dip, and we would see that all of our electronics would literally just turn off. So this reactive power term is incredibly important to the health and maintenance of the grid. Carter.
The brackets to the absolute value or is it the magnitude?
Magnitude.
Magnitude is the value?
Yes. All right. So to put this more succinctly, we can say that in rectangular form, our average power is expressed as simply P plus JQ. Before we move on to the polar form representation, does anybody have any questions about anything thus far? All right, so let's get into polar form then. So in polar form, our complex power would be expressed as the magnitude of our RMS phasor voltage V times the magnitude of our RMS phasor current I with an angle of theta V minus theta I. Okay. So actually, let me do this in purple as well. So this term right here, just the product of the effective voltage and the effective current, is commonly referred to as our apparent power. So apparent power is literally nothing more than the magnitude of our complex power, right? It's just our complex power where we don't care about phasing. Okay? So because it's the magnitude of the complex power, its units are going to be the volt ampere as well. Okay? So you can know whether you're talking about apparent power versus complex power by whether or not you're provided with a phase angle to deal with, right? So apparent power never has a phase angle. It's just the magnitude of that particular complex number. Apparent power is another very important quantity or concept because that's actually the thing that we use to design AC systems or steady state sinusoidal systems, okay? So I feel like the answer to this question is probably 0 or damn near it. But have any of you guys ever looked into speccing out a generator or something like that for your home? Probably not. Perhaps your parents have. A question that you guys might have actually have an answer to. How many of you guys have tried to buy a UPS for your computer or something like that, an uninterruptible power supply? So if you look at the specs on a UPS or uninterruptible power supply, you'll probably see that it's rated for something like 1800 watts and 2100 VA. That 2100 VA is the apparent power rating for that uninterruptible power supply. So effectively, it's telling you that not only can it handle resistive loads, but can also handle smaller inductive or capacitive loads as well, like a fan or something like that, okay? So we use apparent power to design to because it's kind of like a worst case scenario, okay? What I mean by that specifically is we're taking only the magnitude of our voltage and the magnitude of our current and we're multiplying them together. We're not accounting for any kind of phase difference that could cause the overall power level to fall lower. So this is why we use apparent power as a basis for design. It represents the absolute maximum amount of power draw that we could see using RMS quantities, okay? And then lastly, we have this guy right here. And this is what's commonly known as our power factor angle. And we're going to give this guy a symbol, theta S. Now, one thing that I want to point out here, and we don't know what power factor is yet, but hopefully we will by the end of today, or if not, the very beginning of class on next Monday. Theta V minus theta I should look familiar to you guys. At least I hope it does, okay? Because that angle right there is the exact same way that we define the angle of an impedance. Right? So if we know that our impedance is the ratio of phasor voltage V divided by phasor current I, that complex math works out to where the result of that has an angle of theta V minus theta I. So our power factor angle for complex power and the angle of the impedance is literally the exact same thing. So we'll find out that that is a very quick and easy way, if our impedance is known, in order to characterize the power characteristics of a lot of different electrical loads, like machines and all that kind of good stuff. Okay, so simplifying this down, we could say then that our complex power could be written as the magnitude of S, which is just our apparent power, with an angle of theta S. So I have, within the last 10 minutes, hit you guys with what looks like at least 5 different equations, okay? I know that this can seem overwhelming, but I genuinely don't expect you to remember any of them. A, because you're given an equation sheet, and B, because as long as you can remember what each of these quantities means, your calculator can do all of this for you, okay? So let me explain what I mean by that, okay? So let's work a quick example here. So let's say that I have a sinusoidally excited system. And over here is just some load. And I am able to measure the RMS phasor voltage drop across said load, or the RMS phasor current flowing through said load, like so. And just for the hell of it, let's throw some numbers in here. Let's say that our RMS phasor voltage is 120 angle 0 degrees volts RMS. And our RMS phasor current is, let's say, 6 angle 15 degrees amps RMS. So this load right here would be something akin to like a ceiling fan based on that current value, okay? If we can calculate the complex power using our calculators by simply correctly multiplying those two numbers together, we can take from that any possible thing that we want, okay? So what I mean by that is, let's say that we want S for this load, okay? So that's just going to be V times I conjugate, which would be 120 angle 0 degrees volts RMS times 6 angle negative 15 degrees amps RMS, because the complex conjugate of a complex number just simply changes the sign on the angle. So let's see, 6 times 12 is 72, if my memory serves me correctly. Let me double check that. Yep. So that would be simply 720 with an angle of negative 15 degrees, volt amperes in polar form, or $695.467 minus J 186.3497. So let's call that 350 volt amperes. So if I asked you for the average power, which one of those numbers is average power? The 695.467. What if I wanted the apparent power and the reactive power? Negative 186.350. So realistically, as long as you can put those two numbers in your calculator correctly and have your calculator spit the answer out in polar form and rectangular form, you have access to every single complex power related quantity that there is, right? You have your apparent power because that's just the magnitude of the polar form. You have your average power because that's just the real part of the rectangular form. You have your reactive power because that's just the imaginary part of your rectangular form. And you can calculate your power factor by using your power factor angle, and we'll get into that in a couple of minutes. So there is no need for you to memorize or learn those several equations, because if you can just do that simple multiplication, you have all of that information at your fingertips, okay? So one of the, yes, Teresa. So you don't multiply the angles together, you add them when you're multiplying polar form complex numbers. If you go back to our derivation of complex math, it'll show up that way. So you multiply the magnitudes and add the angles when you multiply. When you divide the magnitudes and subtract the angles. Yes. It's because we're doing the conjugate of I. Yep, so the conjugate operation changes the sign on the angle for a polar form complex number, and it changes the sign on the imaginary part for a rectangular form complex number. For what it's worth, if you can't remember that, your calculator should have a conjugate option in its complex menu so that you don't have to actually remember it. But that is where the negative sign came from. So what I want to introduce next is a handy visual tool for helping you remember what the different parts of the complex power represent. And it is what is known as the power triangle, okay? So this is going to be the power triangle for an inductive load. And we'll explain a little bit more about what exactly I mean by that when we get into power factor here in a couple of minutes, okay? So this is just a representation of our complex power presented on a complex plane. So here on the horizontal axis are our real numbers, and here on the vertical axis are our imaginary numbers, exactly how we wrote down complex numbers when we were learning about them a week or two ago. So let's say that our complex power S would be represented by this vector. Okay. Our projection of S onto the real axis is simply our average power. Our projection of S onto the imaginary axis is our reactive power. The length of this vector is our apparent power. And the angle that this vector forms with the positive real axis is our power factor angle. So to put it again very succinctly, we would see that S is just equal to P plus JQ in rectangular form, or the magnitude of S with an angle of theta S in polar form. And once again, and I cannot emphasize this enough, as long as you know what those different parts represent, this math is a joke because it's just multiplying two numbers together in your calculator, right? I'm sorry, what was that? All right, so let's talk about power factor now. So power factor is, in a sense, a representation of the electrical efficiency of a system, okay? Now, I do not mean efficiency in the way that you're probably most used to hearing it, as a ratio of the output quantity over the input quantity, okay? So if you're talking about, the efficiency of a motor or something like that, that would be the output mechanical power divided by the input power, either if it's an electric motor, in your denominator, it would be electrical energy, or it could be chemical energy if you're burning gas or whatever to get there, okay? So this is something a little bit different. So mathematically, our power factor is defined. So I'm going to have a symbol here, PF, and it's going to be defined as average power divided by apparent power. Now, let me explain to you guys kind of how this represents in efficiency, okay? Average power is what we, as consumers of electricity, actually pay for when we pay our utility bill every month, right? Our average power multiplied by the amount of time in that month is the energy that shows up on our bill, okay? So this is energy that we have consumed in some way, shape, or form. Well, our apparent power is just the magnitude of our complex power. So that is the energy that the electrical utility pays to produce. So let me explain what I mean by that specifically. So it could be a direct cost, meaning that they have to pay for fuel like coal or liquid natural gas to burn in order to spin their turbines and generate the electricity. Or it could be infrastructure costs, like the costs of cabling and wires and conductors and all of that kind of stuff to get power from point A to point B in their distribution network. But anyway, average power is what we pay for. Apparent power is what our utility produces. So it should be fairly obvious, but the utility wants the ratio of those two quantities to be as close to one as possible so that they're not pissing away money, okay? So if our home were operating at a very low power factor, essentially what that means is they're sending a lot of power our way, and then we're sending the overwhelming majority of it back because we've got too much energy storage, okay? So that's what a low power factor means. A high power factor, or as close to one as possible, means that we're taking in almost all of the power and energy that they are producing and utilizing it for something, okay? So while this ratio right here is the fundamental definition, it's actually not the one that I prefer because it doesn't contain quite as much information as I would care for, okay? So another way to represent our power factor is if we scrolled up and we looked at our expression for average power and our expression for apparent power, we'd find that the V effective times I effective cancels out, and we're just left with cosine of theta V minus theta I, or cosine theta S, our power factor angle. So that's literally why theta S is called the power factor angle. It allows us to directly calculate our power factor. So we can see that since our power factor is related to a cosine function, its value is always going to range from +1, meaning that we're operating at effectively 100% efficiency, or we are absorbing 100% of the energy the utility is supplying, down to -1, A -1 power factor simply means that instead of we are absorbing all of the energy that the utility is supplying us, it means we are supplying all of the energy back to the utility. So a negative power factor really just means that we assumed the wrong direction for power flow, okay? The bad case is when our power factor is close to zero, or zero is actually the worst case scenario because that means 100% of the energy that the electrical utility was producing for us got sent right back to them. We didn't actually use or consume any of it, okay? So I want to talk about different cases that we are going to see, okay? So let's start by saying theta S is equal to 90 degrees, okay? So when theta S is equal to 90 degrees, this means that we are operating at a power factor of 0, okay? This corresponds to a case where our load has no resistance and a positive reactance, meaning that we have a pure inductor, okay? So our load in this case would just be simply an inductive energy storage element. So for this particular load, we operate at 0 power factor. Now let's say that instead of being exactly 90, it's just somewhere between 0 degrees is less than theta S is less than, sorry, let me draw that better. Oh, and that looks too much like an angle symbol. 90 degrees. So in this particular case, our power factor is going to range somewhere between 0 and 1, okay? So these cases would be where our R is positive and our reactance is positive. Oh, actually, let me make a note out here. So this is just what we would call a regular inductive load, okay? So whenever we have an inductive load, we know that our current is going to wind up lagging our voltage waveform. And so we're going to call these power factors lagging power factors, meaning simply that our current is lagging our voltage. So realistically, unless your power factor is exactly 0 or exactly 1, you would typically only be able to fully quantify your power factor if you told me not only its magnitude, but also whether or not it was leading or lagging. So we can see from this relationship right here that essentially anytime our power factor angle is positive, we are going to have a lagging power factor, okay? If we continue on, let's consider a case where theta S is equal to 0 degrees, okay? So if theta S is 0 degrees, that means that our power factor is equal to 1. This is also sometimes called a unity power factor. Unity power factor is neither leading nor lagging, and it represents, again, 100% efficiency on our system. So this is the case where our resistance is positive and our reactance is 0. So we would have just a pure resistance. If theta S lies between -90 and 0 degrees, we once again have a case where factor is going to be between 0 and 1, but now it's going to be leading. So our current is going to wind up leading our voltage in these systems. This occurs when R is greater than 0 and X is less than 0, meaning that we have a capacitive load, so some combination of resistance and capacitance. And then lastly, we have the case where theta S is equal to -90 degrees. And so this gives us a power factor exactly equal to 0. So this is where R is 0 and our reactance is negative, or a pure capacitance. So what I'm expecting from you guys to really glean from this, the important highlights, is essentially whenever your power factor angle is between, or whenever your power factor angle is positive, you know that your power factor is lagging. Whenever your power factor angle is negative, you know that your power factor is leading. And to calculate your power factor, it's literally just cosine of theta s. Okay. If you can remember those three things, you're good. Sure. So power factor is simply cosine theta s. If your angle is positive, you have a lagging power factor. And if your angle is negative, you have a leading power factor. So if we go back to that previous example that we worked a couple of minutes ago, just for the hell of it, how would I find the power factor of this particular load? This isn't supposed to be a trick question. Cosine of negative 15 degrees. So what's the cosine of negative 15 degrees? (0.96 and some change. And is that power factor leading or lagging, Matthew? You are incorrect. It is leading because that angle is negative. That is as hard as it has to be. It's literally just take the cosine of the angle of the complex power to get your number. And then if the angle is negative, you have a leading power factor. And if the angle is positive, you have a lagging power factor. That's it. All right, so you guys have about 20 minutes left to work on your ICA. Realistically, I think you should probably just skip problem 1 and jump into problem 2, because I feel like the complex power relationships are more important than the effective value thing.